Yes.
The last talk of the session will be given by Yu Song. Title is Nematicity in a local moment ion chalcogenide, the potassium ion silver tellurium system. So please, Yu.
Yeah, thank you, Qimiao. It is truly a great pleasure to be able to present at this wonderful symposium after a decade of research on ion-based superconductivity. So the topic of my today will be focusing on this local moment system which exhibits nematicity. My name is Yu Song, and I'm from Zhejiang University right now. This work, however, was mostly done during my postdoc at Berkeley. And the results are mostly described in these two publications. All right, first off, I'd like to thank all of my collaborators. The experiments were done at Oak Ridge National Lab and also NIST Center of Neutron Research. The samples were provided by Chadmir Petrovich's group at Brookhaven and also Edith Bourret's group at Berkeley Lab. And we also had collaboration from Beijing Normal University. So as we all know, there are several different phases in the ion-based superconductors. And their parent phases are somewhat different, actually. These 11 system and the 122 and the 11 have parent phases that exhibit nematicity while being metals, whereas this alkaline metal ion chalcogenide system have parent phases that are insulators with some kind of ion vacancy order. So the compound that I'll be talking about today is hopefully will provide some kind of a bridge between the parent phases of these two apparently rather different systems. All right, so nematicity, I'm sure everyone here is all very familiar with this topic. It was first revealed through resistivity measurements under strain. The proposals for understanding this behavior is either a spin nematic in which you have spin correlations that break the orbital rotational symmetry, or you have orbital ordering breaking the same symmetry. And experimentally, you see actually both phenomena. Either you see in elastic neutron scattering, you see this anisotropy of spin excitations as 1, 0 and 0, 1. And in our case, you see a splitting of dxy and dyz and d xz orbitals along the gamma x and gamma y directions. So a common feature of this electronic nematicity is basically you apply a very small perturbation, and very often this is strain, and you see a rather large response in some kind of electronic response, either spin or electronic structure. And another important question in this field is the role of electronic correlations. And since very early days, we know that these materials are intermediately correlated, similar to the lightly doped cuprate. And however, compared with cuprate, there's an additional degree of freedom, which is the orbital dependence of the electronic correlation, which the xy orbital be much more correlated to the information of the other orbitals. But there's also a system dependence from the phosphide correlations. So this then raises a very natural question: is in the description of the various behaviors of these materials, should one focus, or should one start from a itinerant or a local moment approach, or put it in another way, should one focus on the coherent part of the spectral function or the incoherent part? With regards to superconductivity, there's a very interesting research, rather comprehensive study, which looked at the Fermi surface and the superconducting transition temperatures of various systems of the ion-based superconductors. And the findings that for systems with very similar electronic structure, the TC can be dramatically different. Or for systems with very similar TC, the Fermi surface can be dramatically different. So this observation led to the proposal that perhaps the electronic structure at the Fermi surface alone is not sufficient to describe all of the physics of these different series of materials. And so this led to the proposal that perhaps the localized physics should also be taken into account for a unified description of the various systems. So the approach I'll be taking today is somewhat unusual. I'll be looking at an analog material, which itself is not superconducting, but hopefully by examining its behavior, some insights nonetheless will be gained in relation to the physics of the ion-based superconductors. All right, so the outline of my talk will be divided into the following sections. Firstly, I'll describe the physical properties of this compound, this KF18 material, and then I'll show that it actually exhibits some ordering as well as nematic ordering. And then, interestingly, it has a magnetic order that is what I call a stripe-like helical magnetic order, and I'll describe what that means. And then I'll show that it responds to strain, as well as there's a nematic stability very similar to the ion-based superconductors, followed up by a summary. All right, so this material was actually first reported in 2011 by Chatmir Petrovic's group. And from the susceptibility measurements, this material is a very nice local magnet with a very nice Curie-Weiss behavior in the magnetic susceptibility. And in the resistivity, it's a semiconducting or insulating-like transport behavior. And then RPS was also done on this material, showing a sizable gap of several hundred MeV below the Fermi level. And in addition, we have also carried out optical measurements of this material and show that there's no Drude peak consistent with the RPS measurements. And in addition, this optical measurements are actually bulk sensitive. So this basically means that the insulating behavior is in fact a bulk behavior rather than some surface effect. So in summary, this compound, the physical properties seen through various probes basically tell us that this is a bulk insulating magnet with an effective spin of roughly equal to 1, and also a transition into a magnetic order state around 35 Kelvin. This can be seen in this anomaly here. All right, so the crystal structure of this compound in the initial report was suggested to be isostructural to the 122 compounds, for example, barium iron arsenide. And when you look at the powder data, for example, it actually fits very nicely with this structure. And in this structure that was initially proposed, the silver and iron atoms are disordered. But this seems to be at odds with the fact that this system exhibits long-range magnetic order, because if you have disordered magnetic and non-magnetic ions, then it's a bit unusual, it seems, that there can be long-range magnetic ordering. And then we thought of a related work that we have done during my PhD at Rice with Punching and Chimiao, which is we looked at this compound, the sodium ion copper arsenide. What we found there is that even though when the powder diffraction, even when you do powder diffraction, it can be described by a disordered system. When you measure it with single crystal, you actually see the transition metals are actually ordered. So this basically suggested to us that even though despite the report from the earlier work, the iron and silver in this compound may very well be ordered. So this then led us to do a single crystal measurement on this material, and indeed we saw a whole bunch of superstructure peaks. All of these additional peaks away from the grid points are actually superstructure peaks. So this basically led us to show that in fact, there is transition metal ordering in this system, and they are basically can be described. This superstructure peaks can be described by two kinds of mirror domains, with the iron atoms forming this kind of 2x2 block structure, which are separated from each other by these silver atoms, which are non-magnetic. So this structure is actually very similar to this 245 phase in the alpine metal iron chalcogenide. This phase, for example, potassium ion. So you see, we basically have the same kind of structure in itself.
Can you be closer to the mic?
Is it good? Is it good now?
This is okay. This is very good now. Yeah. Thank you.
Okay. All right. Yeah. So, so basically they have the same kind of unit cell, but in the 245 phase, the ion blocks are much closer to each other. They're actually directly connecting. But in this case, they're much further apart. All right. So, so in addition to this structural ordering of the iron silver, I actually have evidence for a nematic order in this system as well. So before going into the data that we have, I'd like to review the results in the case of the barium iron arsenide in single crystal studies. So in single crystals, you actually have 4 types of structural domains shown on the left here. And then when you look at the diffraction pattern in the AB plane, then you actually see that depending on where you measure, you have quite different patterns in the reciprocal space. For example, at 220, you have these 4 peaks, which are organized this way, whereas at 200, you have 3 peaks organized like this. So they're quite different. So in our case, this is a structural measurement. We see some changes at the magnetic transition temperature around 35K. So this tells us that there's a structural transition here. And then when we do various scans at 200 and 220, very much similar to what was done in the case of the barium iron arsenide, what we saw was that there's clear splitting along the 220 transverse and longitudinal directions, whereas along the 200, only the transverse direction shows some clear broadening, whereas along the longitudinal direction, there's very little broadening, little or no broadening. So this basically led us to propose that the structural transition that occurs in this compound predominantly happens along the ion-ion direction. And it's the same kind of structural distortion that happens in the ion-based superconductors, which is that the 2 directions, one of them becoming 1 minus delta times some original lattice spacing, and the other becomes 1 plus delta. And then by fitting the actual peak splitting, we're able to extract the magnitude of this distortion. And it's basically 10 to the minus 3, which is in line with all of the other ion-based materials. They're all in the same order of magnitude. So this is something that's quite interesting to us and basically suggests that the structural transition that we see in this material is very similar to the ion-based compounds, the ion superconductors, and suggesting that the same kind of nematic order is at its origin. All right, so so then when we look at the magnetic order, it's actually quite different. So it was actually characterized by this incommensurate propagation vector. So this seemed somewhat strange because in the case of the ion-based superconductors, the magnetic order is usually accompanied by some stripe type magnetic ordering. So in this case, in the case of the KF8T compound, this is actually some kind of helical magnetic order. So for a helical magnetic order, the description of the spins as a function of the atomic position in real space, basically you have a sine or cosine modulation of this of the spin described by this propagation vector as well as the its position in real space. However, there's also a additional phase factor that you can play with when you have more than one spin in the unit cell. So in this case, we have 4 spins in the unit cell. And if this phase factor forms a stripe type configuration, then what happens is that when you look at the structure of overall, is that even though when you look at the same site across the whole crystal, for the same site, it's actually modulated in a helical fashion. But when you look into each block, they actually form this stripe-like configuration within each block. So this is what I mean by a stripe-like helical magnetic order. So this then gives additional evidence that this is indeed very similar to the ion-based superconductors. Even though this helical magnetic order, it also has some flavor of the stripe spin configuration seen in the ion-based superconductors. And then we have also shown that there's another additional connection between these systems, which is that in the case of the ion-based superconductors, the distortion is elongated along the antiferromagnetic direction and contracts along the ferromagnetic direction. And we saw our detailed analysis basically shown that this is also the case in this KF-AT material. So in addition, there's some additional similarity, which is a bit nuanced, but let me try to go through it nonetheless. So here, we show some magnetic stability measurements of this material. So this is a directional measurement with different fields applied along different directions. So we see that the in-plane direction seems to be isotropic, whereas the C direction seems to drop a lot more in the ordered phase. So this seems to suggest the C-axis is an easy axis. However, when we apply a strain to detween the sample, we actually see that the in-plane direction, the A-axis, the A direction also drops a lot compared to the B-axis. So these two results basically suggest that this is actually an easy plane system spanned by the in-plane A-axis as well as the out-of-plane C-axis. So this is actually also similar to the case of the ion-based superconductors. And the way that it is basically shown here in this polarized inelastic neutron scattering measurements. Here, the A-axis is lowest in energy because that's where the ordered spins lie. And then we look at the fluctuation spectrum. You see the C-axis polarized spin waves are actually lower in energy. So in both cases, if you assign a energy scale to the magnetic, to the spin anisotropy, then you have, there's the largest, it costs the largest energy for the system, for the spins to lie along the B-axis, and then smaller energies for them to lie along the C or along the A-axis. So they can be described by the same hierarchy of spin anisotropy in both cases, in the ion-based superconductors, as well as this KF-AT compound. All right, and then we'll show the, we'll try to probe this material, the strain, which is a very natural idea given the similarities shown in the previous slides. So the method that we take is this approach first pioneered by Christophe, the mine gas group, which is to glue a sample onto a substrate, which has a differential thermal contraction when you cool it down. So the way that's done is because you have some glass fibers in these plastic substrate, and then it basically have a differential thermal contraction upon cooling. So the first thing we saw is that when we measure this with neutron scattering, rather than broadening of these peaks, as shown before for the twin sample, you actually detween the sample. Because when we measure two orthogonal directions, you see one of them moves to a smaller scattering angle, and the other moves to a higher scattering angle. And then when we look at the magnetic peaks, we also show that they become detweened. So one of them is much more, has much more intensity. So both the structural and magnetic measurements show that the sample is detweened. So strain effectively detweens this material. And then we look at the structural distortion. So we compare with the freestanding sample, show that the structural distortion is kind of smeared out, even though you can still see a clear kink here. Then when you look at the magnetic order parameter and compare it with the freestanding sample, you see that the magnetic transition is also enhanced somewhat. And this is actually also seen in the susceptibility measurement. You see the peak of the magnetic susceptibility actually increases under strain. So this is actually also similar to the measurements in barium iron arsenide. Once you apply strain, the transition temperatures increase. So these again is another similarity between these systems. All right, so the well, with this measurement of the magnetic stability under strain, we can actually obtain this parameter, which is some kind of stability anisotropy, and combined in combination with the structural anisotropy, which is this quantity, we can actually obtain the ratio of the two, and this is kind of a nematic stability. So this is actually the same. almost the same quantity that was measured by Junhao using resistivity. And there, this anisotropy is defined using resistivity. And of course, it's the derivative of this quantity that was reported in that case, whereas here we're directly probing the ratio of the two. Of course, in the linear response regime, these two would be identical. So what we have here is basically shown that there's also a large pneumatic susceptibility. It also has a sort of a divergent behavior approaching the transition temperature. And as discussed in this pioneering work, that this divergent pneumatic susceptibility provides very strong evidence for the electronic origin of the structural transition. And this also applies to the measurements that we have done for this KFAT material. So what is the understanding for this nematicity in this compound? A very simple way to look at this is to take a local spin approach and define this kind of an autoparameter for each of the ion 2x2 block. And this is basically the same kind of approach taken for the ion-based superconductors, except for there you have defined it for the lattice rather than for a spin block. So depending on the spin configuration, you can have two kinds of stripe configuration. They correspond to this phi parameter either being larger or smaller than 0. So basically our observation of this susceptibility anisotropy basically shows that there's a non-zero autoparameter phi. And in addition to observe this anisotropy in susceptibility, we need to be anisotropy in spin space. So basically, all of these points to the spin pneumatic scenario proposed for the ion-based superconductors provides a reasonable description of the pneumatic state that we see in this KFAT material. And interestingly, this susceptibility anisotropy is actually also predicted for the ion-based superconductors in the tetragonal paramagnetic state once you apply strain to it, but it's not been observed. And there, possibly, the reason is that the spin susceptibility is just inherently too small. Whereas in this case, because it's a local moment with a fairly sizable moment, then it's much easier to observe this directly. All right, so now this is a very interesting material, but perhaps somewhat more intriguingly is that this is actually a part of a very large family of materials, and this is this compound is actually one of the, you can see a very large number of materials. But what's interesting about this particular compound is that it's filled among many most of them are actually spin glass ground state, whereas this one has a magnetic order. So a possible reason for the spin glass ground state is actually could be seen when comparing these two potassium iron silver tellurium compounds. When you change the ratio of the iron and silver, you actually change from a spin glass state to a AFM state. So possibly many of these compounds may also have a magnetic ordered ground state once you have the suitable sample growth condition or the ratio of the two kinds of atoms. And then actually, this is not just limited to iron. You can actually have cobalt in iron's position, as well as manganese, and also chromium. And also you can have the sodium variant of these materials, which is not the case for the iron-based material. Whereas once you have sodium, then change to the 1-on-1 phase. All right. Oops, what's going on here? Okay. All right. So there's a large number of analog materials. So it really parallels the 1 to 2 families of iron-based superconducting material, where you have, for example, the barium cobalt arsenides or the barium manganese arsenides. And currently, most of these studies are done. The structure of most of these materials are only reported based on powder XRD. And as I discussed previously, even if there is some kind of atomic ordering, you may not see it using powder XRD. So potentially, this is a very large family of quantum materials which may which may have some interesting behaviors and possibly even superconducting states if careful examinations are dedicated to these materials. So, okay, in summary, our findings basically show that this insulating material, this insulator with a very large gap and large moment as well, it exhibits a coupled stripe-like magnetic and metal orders, very similar to the parent phase of the iron-based superconductors. And then, in addition, we show that there's additional similarities, and these include the similarity of the magnitude of the lattice distortion and the way that's related to the stripe configuration. And there's also the similarity of the spin anisotropy, the hierarchy of the spin anisotropy, as well as the way that they respond to strain. And there's also a divergent nematic susceptibility seen through the magnetic susceptibility rather than the resistivity, as shown as most of the iron-based superconductors. And so this then motivates, in my opinion, because of these multitude of similarities, this then perhaps motivates a localized description of the iron-based, at least the parent compounds of the iron-based superconductors, at least to capture these similar, the aspects of these different systems, the similar aspects of these different systems, their common features essentially. And then lastly, the detailed study of this KF18 material represents the potential of a fairly large family of materials, which in the diversity of the compounds really parallels the 1 to 2 family of iron-based superconductors, and perhaps more insights can be gained by looking into these interesting materials. And that is all of my talk, and thank you very much for your attention.
Thank you very much, Yu, for a really nice talk. I see Pen Chen has a hand. Please, Pen Chen.
Yeah, okay. So Yu Song, very, very nice talk. Yeah, so this is very interesting. I haven't paid attention to this compound. Yeah, but anyhow, so you mentioned that your nematic phase, you're thinking is mostly driven by essentially local moment because it's the insulator. So how do you understand then, I mean, the case that it's so sensitive to lattice structure? Because in the case of an iron-based superconductor, you would have imagined that this whole thing is driven by, orbital effect, right? Once you turn the pressure on, and then you have a, splitting of DYZ, DXZ orbitals. And then that induces additional coupling to magnetism. But here, I mean, I don't think orbital plays any role, right? How do you think about the similar type of effect? Actually, the other thing is that can you actually see spin dynamics differences between 10 and 01 in terms of very similar to the case of iron pnictide? Is that also seen? I mean, you haven't shown any elastic data, so I don't know.
Yes. So so the second question. Whether you have different pi 0 and 0 pi fluctuations. So that basically corresponds to this. Once you have a non-zero disorder parameter phi, then you have the difference between those two types of fluctuations. Mm-hmm. So the fact that we see some anisotropy in the magnetic susceptibility is kind of an indirect evidence of that.
Okay.
Yeah. So we have attempted inelastic neutral measurements of this material, and we do see some anisotropy, but the data quality is not. I mean, in the older state, it's very clear that there's strong anisotropy, but in the paramagnetic state, the data quality is not as good as the baryon 1 to 2 that was measured. Yeah, and then to the first question, whether there's orbital degree freedom, I think the orbitals are very likely involved. It's just that the current measurements do not directly probe the orbital degree freedom.
Oh, so you think there's also strong spin-orbit coupling? Or?
Yes, so very likely, I think there's also a orbital ordering, possibly at the transition temperature that occurs at the same, concomitantly with the other, with the structural and the spin ordering. But that has not been probed. Mm-hmm. Yes. Yeah, okay. So the way to measure that, perhaps ARPIS may be a bit difficult because of the insulating nature of this compound. So I've been thinking about doing some X-ray linear dichroism measurements to directly look at the occupation of the two orbitals.
Okay, thank you.
Any other question?
I have one question. Yeah, so for this compound, it's apparently it's like you refer as insulator, and in the meanwhile you have this kind of cycloid or a spiral, this kind of spin order. So I know that you know, for the type 2 multiferro, you know, you have this kind of cycloid order, right? You can get this K and cross product with this kind of propagation like a vector, and eventually get a polarization. So I wonder, you know, that does that mean, you know, this compound is also multiferric, or of course that depends on the details of the spin texture. So I wonder whether, you know, this is true or not.
Yeah, so I haven't really thought about that. But the perhaps one aspect of this material that's relevant to this question is that this compound is actually chiral. The structure of this material is actually chiral. So perhaps this is something to actually think about. So if you look at this mirror, if you look at the structure of this compound, it's actually chiral. So even though when you consider only 2 dimensions, this material is basically these two domains are mirror planes of each other. But once you look at once you consider the tellurium atoms, which actually are situated in between these transition metals, they're actually either all above or either all below the plane for these ion 2x2 blocks. You can again see that just by counting the number of the distance between the Manhattan distance between these these blocks. You'll see that they're all either above or below. So that makes the structure itself chiral. So yeah, and then the structure itself is quite low symmetry. So perhaps so DM interaction is certainly allowed. So maybe then that would facilitate some kind of multiferric or some kind of complex magnetic coupling. Electric magnetic coupling. Yeah, but I haven't really looked into that.
Can I ask a question about the optical conductivity? Can you show that data?
Yes.
So which temperature is the measurement?
Oh, this is just measured room temperature.
Okay, so the transition temperature is, you said 35 Kelvin, right?
Yes, yes.
And I wonder, you know, like in the ion-based superconductors, the nematicity, the nematic order affects the optical conductivity. Maybe Joel could correct me if I'm wrong. If you don't apply any stress, can you already see the effect of nematic order on the optical conductivity, or do you have to apply external stress in order to see that?
So without stress, I mean, for most of the optical conductivity paper I know of, they're measuring iron tides, and it's very close to the magnetic transition. That certainly has a huge effect on the optical conductivity.
It's dominated by
right.
But
so
I see. That's not necessarily a well-defined question.
Yeah.
But maybe just coming back to this here, I guess the question is, if the orbitals are involved, I would suspect that when you go through the transition, the optical conductivity should be strongly affected, and even at high energies, depending on, I suppose, the crystal levels. So I wonder whether that's one way to probe that.
Yes, yeah, I certainly agree that that's a very that's something that certainly needs to be looked at. Mm-hmm. Yeah, but we haven't gotten to doing that yet.
But do you have some suspicion about how big these crystal levels are, these various orbitals?
No, not at the moment. No.
Mm-hmm. Maybe even neutron scattering would be useful for that.
Right. So in our measurements, we basically measured up to 1 eV, and we didn't see clear crystal field excitations.
Mm-hmm.
Yeah.
For
so
iron,
if it's
for iron, it's very difficult. Yeah, it's a very high energy.
I see. Okay. But it seems like maybe come back to this optical conductivity question. Maybe if you apply some external stress and see how the anisotropy respond to how high energy that the optical conductivity responds to the transition, it might provide. I mean, like in the pnictides, it could go all the way to like half of electron volts or even larger frequencies.
Right.
Yeah, so something along this line might be informative from the...
Yes, I agree. Thank you. This is a very good suggestion. Yeah.
Mm-hmm.
Well, we'll try to look at that.
Mm-hmm. Okay. Any other questions, comments?
Can I ask a question?
Yeah.
This is Ron Yu from Renmin University. So you said that this is an insulating compound, right?
Yes.
So is there any like this resistivity data, and one can extrapolate how big the gap is?
Yes. So this is actually the resistivity data. So if you try to extract a gap value from the high temperature value, the gap is actually fairly small. It's like less than 100 MeV. But when you measure RPS, for example, it's quite a bit larger. Mm-hmm. Yeah. So this seems to be a common feature of many of these systems. For example, the sodium ion copper arsenide that we looked at, and a bunch of the materials I showed towards the end. When you look at the resistivity, many of them actually have very small resistivity relative to their bulk gap seen with spectroscopy. So that's actually something that's I guess it's not really understood why that is.
Mm-hmm. And also, if you look at this optical conductivity data, and the gap is consistent with the RPS or with the resistivity? I
guess it's more consistent with the RPS, because this wave number like 10,000 is roughly like 1 eV, right? So
I see. Okay.
So I guess we look at the peak, it's like around 1 eV. So here, it's like roughly half eV below the Fermi level, and then maybe the same magnitude above Fermi level. Then it's around 1 eV as well in RPS.
Okay, thank you. Mm-hmm.
Yeah.
So I know Johanna has raised her hand, but can I quickly follow questions on the resistivity? So since the resistivity is actually measurable at the temperature of the nematic transition, did you try to measure resistivity and anisotropy and then see anything from that?
Yes, we tried, but we did not really see any clear signature. So one possibility is that these resistivity dominated by a very small activation gap may not be intrinsic to the gap. Maybe it's due to some defects or some extrinsic behaviors. So maybe it doesn't reflect the,
Yeah, so probably kind of like a hopping type of conduction.
Yeah, some in-gap states.
Right.
Mm-hmm. I think Yona is patiently raising her hand, please. Are you still there?
Hello?
Yeah,
hello.
Excellent.
It's your turn, please.
Very nice talk. Could you show the pseudo-nematic susceptibility data again? I was just wondering, below the transition, I noticed it changed sign. Do you have any motivation for why? Because you don't see that, I think, in the, like, say, 122 systems.
Yes. So a fairly intuitive reason for why it would change sign is that this spin susceptibility, when you just consider easy access system, in the paramagnetic state, the easy axis will give you a large susceptibility because the spins like to stay along that direction. But in the order state, it actually gives you a small susceptibility because all the spins are already ordered along that direction. So I think this is kind of common to magnetic systems. Yeah. So then this sign change actually provides evidence that this anisotropy we see above the transition temperature is actually due to fluctuations rather than static order.
I see. Thank you.
Yeah. Thank you.
Great. Any further questions or comments? It's getting late. So I think I don't see any hands raised. So at this point, thank you again, you, for a beautiful talk, and thanks to everybody in this session. Yeah, for a very nice session.
Thank you.
All right. Is Ming still here? Hi, Ming.
Oh, I'm here.
Yeah, are we on our own in terms of uploading?
I haven't heard from Jenny today. Do you?
I didn't hear.
I can stop recording.